Hi, I'm Anna Boylan, and I will be presenting on Rocky Mountain snowpack and change in snow patterns over time. Here's a quick overview of what this presentation will cover: introduction, study area, my methods, my results, and some discussion and conclusions. So my project revolves around snowpack in the Rocky Mountains and how snowfall and snow accumulation may be changing along with climate patterns such as precipitation or temperature. But why is this important? So Colorado is a headwaters state, meaning that it harbors the beginning of a major river basin. The Colorado River begins just north of Winter Park in Granby, Colorado in Rocky Mountain National Park, which is highlighted in the black box on the screen. The water stored in the snowpack here eventually results in spring runoff, which ultimately feeds many ecosystems, farms, communities, and much more as it travels from here to the Gulf of Mexico. Climate change is impacting the amount of precipitation falling as snow, which is a major resource for the drought-impacted Colorado River Basin. It is estimated that annual mean discharge of the Colorado River has been decreasing by 9.3% per degree Celsius of warming because of increased evapotranspiration, which is mainly driven by snow loss and a consequent decrease in reflectance of solar radiation. So basically, less snow means less water to begin with and more evaporation of water that is traveling in the river basin. And so in this presentation, I'll mention two different measurements: SWE, or snow water equivalent. This is the amount of water stored in the snowpack available for runoff. And then snow depth is a climate change indicator and provides a lot of insight into precipitation and atmospheric conditions. So moving on, this graph shows where we currently stand in terms of SWE, or snow water equivalent. This is from February 26th, but it's probably pretty similar for the date right now. So you can see that most of Colorado is hovering around average for snow water equivalent, but the southern portions of the state are quite below average for the amount of snow available for runoff as we come into this summer season. And then these next few graphs, they show or just help to illustrate the idea better and provide more background. This graph on the left shows changes in snowpack length. In much of the western US, snowpack is present for shorter amounts of time, resulting in earlier runoff and possibly less water available during the most drought-intense months. The top graph on the right shows a similar idea where peak snowpack is occurring earlier in the season, again resulting in earlier runoff and less water when it is needed the most. And then finally, the graph on the bottom shows a trend of declining stream flow in the Colorado River, especially in the middle Rocky Mountains. And this may be due to changes in snowpack. And so this is really why I chose to study this, not only because it's interesting, but it is really important for our water and water moving across the West, which is just a really big concern with climate change and warming temperatures. I also have a pretty personal connection. I'm currently living in Grand County, right outside of where the Colorado headwaters are located, and I do a lot of studying of snow and tracking weather, and so it's just really interesting for me to pair that background with this project. So for my project, I wanted to address a few main questions. These are the 4 research questions that I aim to answer with this project. So 1, how has snowpack in the Rocky Mountains changed over time? 2, how has the pattern of snow distribution changed over time? 3, what is the relationship between snow depth and snow water equivalent? And 4, do climate-related events such as precipitation or temperature impact snow depth over time? So like I said, my study area for this project was Rocky Mountain National Park, and I used a boundary from Estes Park basically to Grand Lake, which you can see in the bottom left corner of the map. And so the climate in Rocky Mountain National Park is pretty moderate, with most of this moderate weather occurring at the elevations below 9,400 feet, but higher elevations are pretty typical of mountain weather with a wide variation between day and nighttime temperatures. The average precipitation is around 13.10 inches of moisture per year, which is in Estes Park, but as you move closer to Grand Lake, this increases with around 20 inches per year. The terrain is pretty varied. It is one of the highest national parks in the nation, with elevations from 7,860 to about 14,000 feet, and the park contains 60 mountain peaks higher than 1,200 feet. The Continental Divide runs north to south through the park, and there are many different areas or ecological zones from montane to glacial. And then this park was shaped by glaciation rather than tectonic movement, and it has a base of granite, igneous, and metamorphic rocks. So now jumping into my methods, I began with site selection, which I just touched on. From there, I decided to pick more recent dates to understand current conditions of snowpack. So my first image will show March 4th, 2017, and my second image will show February 28th, 2024. And then I went into image selection. I found that data availability really dictated the specific dates that I was able to use, just in terms of cloud cover and image quality. But I was able to use Landsat 8 and 9 imagery to conduct my analysis. And then once I found suitable images, I went into my analysis, which I will go into further in a few slides. So my highlighted feature is snow. These two images show 2017 and 2024. The pink shows the presence of water and snow as it is highly reflective. The green shows vegetation and other landscape types. I chose my bands just because it highlights the difference in vegetation versus water better than any of the other band combinations that I explored. So now getting into some of my analysis, I chose to use the NDSI, or Normalized Difference Snow Index, to show change over time. This index uses visible and shortwave infrared reflectance to identify snow cover. NDSI uses values from 0 to 1, with 0 indicating no snow and 1 being full snow coverage. So, to calculate NDSI, I first clipped my original images to encompass the area that I wanted to analyze. These two images show my clipped imagery for 2017 and 2024. From there, I calculated NDSI using the raster calculation showing at the top using bands 3 and 6. These two images show the final NDSI analysis with 2017 on the left and 2024 on the right. You can see that the pattern of snowpack distribution did change between these two time periods. In 2024, the NDSI image shows that the lower elevation areas and regions closer to the Front Range and east of the Rocky Mountains, which is the right portion of the image, may be receiving less snow, and this area of low snowpack is growing and moving further west. So from there, I reclassified my data to show either snow or no snow for both 2017 and 2024. The same pattern exists where warmer and drier conditions are moving further west. You can see that that white area on the right side of each image is growing in the 2024 photo. However, in 2024, there seems to be deeper snowpack, especially in the left upper corner of the image, and more snow coverage in general, which was interesting and surprising to me when I conducted this analysis. So from there, we can look at my change detection image. The image on the left shows where snow coverage change has occurred. For this image, I subtracted 2024 snowpack values from 2017 values. And then the image on the right is using a base image from 2017 with the change detection map overlaid. So you can see that there was change quite a bit. However, the patterns, it shows similar snowfall in similar regions, with 2024 maybe exhibiting some more snowfall and definitely a different distribution of snowfall. And then finally, this next slide shows my unsupervised classification of my study area. I decided to use LVQ means as my analysis method as it showed the most variation in land cover type. You can see that there's quite a difference between my before and after images in terms of land cover type and where that's occurring. This is suggesting that over time, the pattern of snowfall and precipitation accumulation may be changing. So from all of this, I drew two main conclusions. The first one is that snowpack is in fact changing in the West. These patterns are hard to distinguish only using 2 years, just because climate, obviously you need more time and a longer time base to really determine if patterns are occurring due to climate-related issues. So in the future, I would like to use more data and more different dates across, a wider spectrum of years, just to determine if climate is in fact having an impact on snowpack depth and the water available for transport as runoff. And then my second conclusion is that the pattern of snowfall and snow accumulation is different from 2017 to 2024. Like I said, you could see that drier, less snow infiltrated area on the right of these images was getting bigger and moving more west. And so this may result in runoff patterns and ground infiltration patterns changing as well. And this could mean sending water to places where it hasn't been in the past. And these areas may not include the Colorado River Basin, which would have dramatic impacts. So what does this all mean in terms of the big picture? So for policymakers, we need to have more partnerships with researchers and water managers, maybe more insight into how legislation can be used to manage and protect water resources for future generations, or how we can use greenhouse gas reduction goals to help with climate change and changing precipitation. For water managers, more increased assessment and management of water resources and recreation, just to better manage water, especially if it's becoming less over time. And then for science and research, this understanding of the connection between snowpack, runoff, stream flow, available water resources, and climate change is new. And there's not a lot of information or a lot of understanding about how all of these things are connected. So, this idea could be a really good jumping off point for more science and more research into this topic. And then just for recreators and the general public, more awareness of natural resources and human impact on water resources and how our water is transported, where it comes from. Just more knowledge base surrounding that would definitely help with understanding snowpack and how it impacts all aspects of human life. So that is my project. Thank you for listening. If you have any questions, please reach out. Thanks so much.